Now we're starting lenses. There are mainly two types of lenses. These are converging lenses or convex. These are called diverging lenses or concave. Now some technical terms about lenses. First is the optical center. Now we'll take a converging lens for this. So the optical center is the center of the lens. Then next is the principal focus or the focal point. The focal point is a point at which all the rays passing through a converging lens seem to converge, and there is a focal point on both sides of the lens. The focal point is in line with the optical center of the lens. These three are concurrent. These three are collinear. So now if a ray passes through the lens, it will converge towards the focal point. And if we had a diverging lens, then when these lines would diverge, they would be such that it would seem that they are diverging from the focal point. Next is the principal axis. The principal axis is a line passing through the optical center of the lens. It is a vertical line. So if this is the optical center, this is the principal axis. The focal length is the distance between the focal point and the optical center, and magnification is the ratio of the image size upon object size. Now we'll do some cases of the converging lenses, but first we'll learn three types of rays that can be formed or drawn. Now the vertical line is the principal axis of a converging lens. These are the two focal points, and 2f is twice the focal length. If we have an object over here, we will draw rays from the top of the object. The first type of ray is such that it travels from the top of the object through the optical center of the lens. The second type of ray first travels parallel to the focal length and then converges towards the focal point. Now the third type of ray first passes through the focal point on the same side of the lens as itself, and then it travels parallel to the focal length like this. All of the three rays meet at the same point, and here the image is formed. So we will be using the first two types of rays, the one that goes to the optical center and the one that travels parallel first and then passes through the focal point. Now we're starting the first case of the converging lens. In this case, the object is placed within the focal length. That means between the optical center and the focal point. So for example, the object is over here. Now the first ray that we'll draw will pass through the optical center of the lens. And the second ray will first travel parallel to the focal length till the principal axis, and from the principal axis it will converge towards the focal point. Now here you can see that these two rays are diverging from each other. So in this case what we do is we back produce these two rays as dotted lines, and where those two dotted lines meet, that is where our image is formed. This is the object and this is the image. Now the nature and the features of this image. Since this image is on the same side of the lens as the object, it is virtual. A virtual image is one that cannot be produced on a screen. So whenever the image is on the same side of the lens as the object, it is virtual. Now we can see that the height of the image is more than the object, so it is magnified, and the image, the top of the image in both cases is at the same end, so it is upright. Now every time if there is a virtual image, it will be upright, and if the image is real, it will be inverted. That is a fact. So this kind of image is formed in a magnifying glass. So that is the use of this case. That is the first case. Now we're doing case number 2 of the converging lens. In this case, the object is placed between f and 2f. For example, this is the object. Now the first ray that we'll draw will pass through the optical center of the lens. The second ray will first travel parallel to the focal length, and then it will converge through the focal point. Now this is the object. Now the features of this image, this is the image and this is the object. Now the features of this image, firstly we can see that this image is magnified. Secondly, this image, this is upright and this is inverted. Thirdly, because the image is on the opposite side of the lens as the object, this image will be real as it can be projected onto a screen. This case is of a projector. That is a magnified image is formed on the projector. This was case number 2. Now case number 3 of the converging lens. In this case, the object is placed at f. So our first ray will pass through the optical center, and the second will first go parallel and then pass through the focal point. Now these two rays are parallel to each other. Therefore, it is believed that they will meet at infinity and the object will be formed at infinity. Now we're starting case number 4. In this case, the object is placed at 2f. Again, our first ray will pass through the optical center. The second will first travel parallel and then converge through the focal point. So now this is our image. This is the image and this is the object. In this case, the image is inverted and since it is on the opposite side of the lens as the object, it is a real image and it is the same size as the object. So for an object at 2f, the image is also formed at 2f. Now this is used in a photocopier machine. So that is the application. This was case number 4. Now we're doing the last case, case number 5. In this case, the object is placed beyond 2f. Again, our first ray passes through the optical center. And our second ray first goes parallel and then passes through the focal point. So this is the image. Now in this case, the image is diminished, that is smaller than the object. It is inverted, and again, because it's on the opposite side of the lens as the object, it is a real image. Now the application for this is in a camera. Now in diverging lenses, there is only one possible case, because wherever the object is kept, it has the same characteristics. Now for example, if the object is over here, the first ray will pass through the optical center. The second ray will first travel parallel to the focal length, and from here it has to diverge in such a way that it seems that it is diverging from this point. So we use these 2 points to draw a line, keeping the scale like this. And we'll back produce this line as the dotted line. Now the image in the diverging lens is formed over here, where the back produced line meets the other ray. This will always be the case in diverging lenses. Now the characteristics of this image: it is diminished, it is upright, and because it is on the same side of the lens as the object, it is a virtual image. In a short-sighted eye, the person cannot see far objects, distant objects. This is because the lens is such that the light is being refracted too much, which is why the image that is formed before the retina. Image is formed before the retina. Now in this case, what we need is that the image has to be formed over here at the retina. So for this, the rays need to be diverged so that when refraction occurs, they meet at this point. Therefore, we will use a diverging lens in case of a short-sighted eye. When a diverging lens is used, the rays diverge, and when they converge at the retina. And one more thing to note is that when a ray is passing through the center of the lens, it is not converged or diverged, it is not refracted, like this one. So in a short-sighted eye, we are using a diverging lens to diverge the rays so that when they are converged by the lens of the eye, they meet at the retina. A long-sighted eye is one which can see distant objects but cannot see near objects. This is because the lens causes too little refraction, and the rays converge behind the retina. So showing that first. The rays converge behind the retina like this. Now for this, we will use a converging lens. Now what the converging lens does is that it brings the rays closer together so that when they are refracted by the lens of the eye, they converge at the retina. So, to correct long-sightedness, so that the person can see near objects, we use a converging lens.